in these two lessons, we will be graphing systems of linear inequalities in order to solve and to identify important information from the graphs. Just a quick reminder of how to graph linear equations. If it is an equation and there's an equal sign, when you put the line on the graph, obviously it is a solid line. But you're going to see many of these will be inequalities. So there's either a greater than sign or a less than sign, greater than or equal to, less than or equal to. If the or equal to is part of the inequality, you will still graph it as a solid line. If, however, there is no equal to, and it's just a pure less than or a pure greater than sign, be sure that you graph the line as a dashed line, showing that that's your boundary, but the points on that line are not actually included in the solution. In order to determine where you shade when there's an inequality, you can choose a test point anywhere that's not on the line, and if that point, when you plug it in, gives you a true statement, that would mean that's the half plane of the line that needs to be shaded. If, on the other hand, you plug it in and it isn't a true statement, it's false, then you need to shade the other part of the graph. We're going to practice these together. It will make more sense, I'm certain, as we go through and do it. So let's get started. And the first inequality we're going to graph is a single equation, or a single inequality, I should say. Y is greater than or equal to 2x plus 1. Now, you have options on how to graph this. It discusses the fact that you could use x and y intercepts for the graph. I'm going to remind you how you can graph using slope-intercept form. So if we look at this, the slope, since this is in slope-intercept form, is 2, because it's always the coefficient that's in front of x when it's in y equals mx plus b form. And remember, you can always turn that into a fraction if you put it over 1. Now your y-intercept is the 1 at the end of the inequality. Y is greater than or equal to 2x plus 1. That means in order to get this graphed, if I choose to put the y-intercept on the graph first, which I would need to do before I can use the slope, that means I go to the y-axis and I put a point at 1 on the y-axis because my line is going to be crossing there. Now since the slope is a positive 2, from here I can go up to right 1, and that gives me an ordered pair 1, 3 that's on the graph. I can go up to right 1 again, and that gives me the ordered pair 2, 5. I now have enough points that I can draw the line, paying attention to the inequality because it has the or equal to. That tells me this needs to be a solid line, not a dashed line. And I will draw in this line. Again, it's much better to use a straight edge. I just don't have that option working with my iPad. Now we need to decide where to shade. So if the ordered pair 0, 0 is not on the graph, then that is a great test point. And when I plug in 0, 0, I get 0 is greater than or equal to 2 times 0 is 0 plus 1. So 0 is greater than or equal to 1. Is that true or is that false? Well, that's a false statement. 0 is not greater than 1. So that tells me I don't shade the side where 0, 0 is. Instead, I'm going to have to shade the other side. So that means I'm shading above this line. And that would be the sketch of the graph. Let's go to the next slide. On this next example, we have another single linear equation. However, this one is not in slope-intercept form. So again, you have options. You could plot the x-intercept and the y-intercept, or you could put it into slope-intercept form and graph it that way. If I want to use intercepts to graph, that means I'm going to put in 0 for x and solve for y. So 4 times 0 plus 2y is less than or equal to 8. And technically we're solving it when it is equal to 8. So if 2y is equal to 8, y is going to equal 4. So I'm going to have my x-intercept at 0, 4. Now to find the y-intercept, I'll find out what x is when y is 0. So if I come back to this equation and I have 4x plus 2 times 0 equals 8. Actually, I put y there. Sorry, that should be an x. Let me correct that. Then I'm going to have 4x equals 8, and x will equal 2. So that means at 0, 4, that's my y-intercept. At 2, 0, that's my x-intercept. I can sketch the line now since I have 2 points. A third point is nice to ensure that we haven't made a mistake, but we do have the correct line here. Now, because of the or equal to, it needs to be a solid line. So I'm going to sketch this in. And now we have to determine where to shade. So again, pick a test point. 0, 0 is the easiest one to use. If I were to plug in 0 for x and 0 for y, I'd have 0 plus 0 is less than or equal to 8, which actually is true. And that tells me this would be where I want to shade. Now, we're going to be graphing more than one inequality at a time because we want to discover where our solution region or our feasible region is. There's a lot of applications in business for this. It's not just one single answer we're looking for. There's going to be a range of values that would fall into the area we might be looking for. So let's practice how we can take more than one equation or inequality and get it on the graph. So the first inequality we see here is 4x minus 3y, which is less than or equal to 9. Let's put that into slope-intercept form. So we're going to have a negative 3y is less than or equal to a negative 4x plus 9 when I move that to the other side. In order to solve for y, I can either think of this as dividing everything by a negative 3. Now if I do that, I have to be very, very careful. Because remember, anytime inequalities are involved, if I multiply or divide by a negative, it has to reverse. So that will turn this into y is greater than or equal to a positive 4/3 x minus 3. Now I can take that and get it onto my graph using slope-intercept form. So it's crossing the y-axis at negative 3. So I'm going to have a point right there. My slope is 4/3. So that means I go up 1, 2, 3, 4, and to the right 1, 2, 3, and I'm at the ordered pair 3, 1. I can count that again. Up 1, 2, 3, 4, right 1, 2, 3. And now I'm at the ordered pair 6, 5. And again, because of the or equal to, that means this will be a solid line. So I'm going to sketch that in. Now, notice there are two other inequalities that need to be graphed. The first one is x is greater than or equal to 0. So when x is greater than or equal to 0, where all of the x values excuse me, are 0, is on the y-axis. And if I want what's greater than or equal to 0, it's going to be to the right of that y-axis, because everything to the right of a vertical line is greater than. Notice we have y is greater than or equal to 0. Well, that occurs on the x-axis, and that means everything that's above the x-axis would be greater than or equal to 0. What I have to determine now is which side of this first line that I graphed needs to be shaded. Excuse me. So again, 0, 0 would be a good test point. If we come back here and we put in 0 minus 0 is less than or equal to 9, is that true? Excuse me, and it is true. 0 is less than or equal to 9. So everything on this side of that line needs to be graphed. This is going to be called my feasible region. That's the region where all of these overlap. Excuse me. Now, one of the most important things we need to know about this is, will this be bounded or unbounded? If it's bounded, it means it's completely enclosed. Notice this thing, the shading up at the top, this is going to keep going on this way forever. Therefore, it's unbounded. But I do have some corner points, and corner points will occur wherever two of these lines intersect. So I have a corner point here, and I have a corner point here. I do not have any other corner points. So it's easy to see one of my corner points is at 0, 0, because that's where those two axes meet. What I need to figure out is, where does this line intersect this line? And the best way to figure that out would be to take the original equation we had, which was 4x minus 3y, which is less than or equal to 9, and what I know excuse me, is that the y value has to be 0 at this corner point, because it's on the x-axis. So if I put in 0 for y, 3 times 0 is 0. And if 4x is less than or equal to 9, when I divide each side by 4, that's going to give me an x value of 9/4, comma, my y value is 0. In our next example, we actually have 4 inequalities to graph. Now you'll quickly catch on to these right here as being helpful to identify what quadrant you're working in. If all the x values have to be greater than 0, that tells me I've got to be looking to the right of my y-axis. If all of the y values have to be greater than 0, I have to be looking above the x-axis. So that tells me that I'm going to be in the first quadrant. And that might be helpful to know when I get ready to do my shading in a little bit. Now, I have 2 inequalities that need to be graphed. This top one, again, you can choose to use intercepts, you can choose to use slope-intercept form. If I decide I want to use the intercept method, I can put in 0 for x and solve to find the y-intercept. So I'd have a negative 2y is less than or equal to 12. if I divide by a -2, now again, be careful. If you're multiplying or dividing by a negative, don't forget you have to flip your inequality. That's going to give you y is greater than or equal to a -6. Okay? Well, and technically, since we're looking for intercepts, the inequality doesn't matter. We're looking for y equals -6, and that would give us the intercept 0, -6. Now to find the x-intercept, we have to put in 0 for y. So we'll have 6x minus 2 times 0 equals 12. And 6x would equal 12. When I divide each side by 6, that gives me x equals 2. So I'm also going to have the ordered pair 2, 0, and that will tell me that I have this point right here, and 0, -6 is down here. So if I sketch this line, I have to figure out which way I'm going to need to shade. Again, 0, 0 is not on this line, makes a great test point. So if I put in 0 minus 0 is less than or equal to 12, 0 is less than or equal to 12, that tells me I need to shade this way. Okay? One more to go, and then we can figure out exactly where we want to draw the shading. So 3x plus y is less than or equal to 9. That one would be easy to get into slope-intercept form if I just subtract 3x from each side. So y is less than or equal to a -3x plus 9. So that tells me my y-intercept occurs at 0, 9. I'm going to put a point there. If my slope is -3, I come down 3, right 1. That gives me an ordered pair at 1, 6. Down 3, right 1. That gives me an ordered pair at 2, 3. And then I'm going to come down 3, right 1, and that'll give me an ordered pair at 3, 0. So when I draw this in, I'm ready now to determine where this needs to be shaded. And so again, 0, 0 is a great test point. If I put in 0 for x plus 0 for y is less than or equal to 9, that's a true statement. So it tells me that I need to be shading over here to the left. And this is my shaded region right there. Now that's how I'm going to get the graph onto the page. What I need to determine now will be is this bounded or unbounded? This is going to be bounded because this is completely closed in. And then I've got to find my corners. And I have a corner here, which is 0, 9. I have a corner here, which is 0, 0. Now, it appears that I may have a corner at 2, 0. How can I be sure it's 2, 0? Well, it means I'm going to need to go back to this first equation, the 6x minus 2y, which is less than or equal to 12, and let's double check. When we put in 0 for the y value, we did get back 2 for the x value. That is a point we had on our graph. So 2, 0 is definitely one of my corners. Now I have one more corner I need to find, and it occurs right here. Okay? That's where these two inequalities intersect. Now I've got to figure out how I'm going to be able to solve to see where these intersect. And I have a couple of options. I can either use something called substitution or elimination, which we talked about in the last unit. So if we were to take this right here and substitute it in for y in that top equation, we would have 6x minus 2 times, I'm going to put in a negative 3x plus 9 for y, okay? And that would be less than or equal to 12. Now remember, we're actually trying to find the equal, so we're just going to put an equal there. And that would give us 6x. A negative 2 times a negative 3x is a positive 6x. A negative 2 times a positive 9 is a minus 18. And that's equal to 12. So I have 12x minus 18 equals 12. If I add 18 to each side, 12x equals 30. And I'm going to come up with x equals, and if I take 30 and divide it by 12, that's going to end up being 5 over 2, because I can take 6 and divide it into 30 and get 5. 6 divided into 12 gives me 2. So that means I've got an ordered pair where the x-coordinate is 5 over 2. We're not done. Now we have to find the y-coordinate. And that means we can plug in to either of these equations. I think you might find it simpler to plug into this one right here. The y is less than or equal to negative 3x plus 9, because if we plug in 5 over 2 for x, once we simplify the right side, we'll know what the y value is. So we're going to get y equals negative 15 over 2 plus, now 9 over 1 needs to be written with 2 in the denominator. I'm going to need a common denominator. So if I multiply 9 times 2 over 2, that means I'm going to have 18 over 2. And a negative 15 over 2 plus 18 over 2 is a positive 3 over 2. So here's my graph. It's bounded, and here are the 4 corners that go with this graph. In this example, we also have 4 inequalities that need to be graphed. The one thing you'll probably notice is this top inequality actually starts with a fraction in it. Now, we can take care of that. If you want to multiply everything in this top equation by 2, we can eliminate the fractions. So we would end up with 3x minus 6y, because I'm multiplying every term by 2, is greater than or equal to 6 times 2 is 12. Okay? Now, I still have to figure out how I'm going to graph this. So I can choose whether I want to use intercepts or if I want to use slope-intercept form. Your choice. This one is a good candidate for using intercepts simply because I notice both 3, which is the coefficient in front of the x, and 6, which is the coefficient in front of the y, will divide into 12 evenly. When that's the case, it's a good option for using intercepts. You won't end up with fractions. So if we plug in 0 for x and solve this for y, we're going to come up with a negative 6y equals 12. Y will equal a negative 2. So that's going to give me 0, negative 2 is one of the intercepts. So 0, negative 2 is down here. Now, let's go back, put in 0 for y. And that means 3x equals 12, so x would equal 4. And we're going to have 4, 0 as the x-intercept. Okay, now that I have those 2 points, I'm going to draw my line. Because of the or equal to, it's solid, not dashed. and I need to figure out which way to shade. If we go back and we plug in 0 and we test this, 0 minus 0 is greater than or equal to 12, that's false. So that tells me I'm going to need to shade below this line. That's not going to be the accurate part to shade where 0, 0 is. I've got to shade the other side of the line. Now, we've got the same scenario with 2x plus 2y is greater than or equal to 14. We can put it in slope-intercept form, or we can use intercepts. So if we put in 0 for x and solve to get this y-intercept, if 2y equals 14, y equals 7. So I'm going to have the ordered pair 0, 7, which is right there. And then we go back, solve for the x-intercept by putting in 0 for y. And if 2x equals 14, then x is going to equal 7. So we have 7, 0, which is right there. And that means this is our line. Sorry, I missed my point just a little bit. And I have to figure out which way I'm supposed to shade on this. So again, if you go back and you test using the ordered pair 0, 0 to see if that's the side we need to shade, 0 plus 0 is greater than or equal to 14. That's not true. So that means I don't want to shade under this line. I'm going to want to shade above this line. And then this tells me if x is greater than or equal to 0 and y is greater than or equal to 0, I'm going to be in this first quadrant. And that means this is the area that needs to be shaded. So we've got the graph. We have to answer the question, is it bounded or is it unbounded? Well, this is unbounded because this is going to continue on this way, all this shading. And I do have some corners. Now, where are the only places that I see corners? I have one right here, and that occurred where this line crossed the x-axis. I know where that is because I went and solved using intercepts, so it means I have a corner at 7, 0. But this is going to be the corner that occurs where those two equations are set equal to each other. Now, by solving for intercepts, I did not end up with an equation that already had y equals something. It's not really set up well for substitution, but I can try using elimination. Let me remind you how that works. If we take 3x minus 6y equals 12, remember when we're looking for that ordered pair, we don't need inequalities. We're going to use equations. And then we're going to have 2x plus 2y equals 14. I think I'm going to multiply this bottom equation by 3, and that will give me 3x minus 6y equals 12 on top. And I'll have 6x plus 6y equals 14 times 3 is 42 on bottom. And now if I add these up, my y's will cancel, and I have 9x equals 54. Do I have that right? And that would mean x equals 6, because 9 times 6 is 54. Now I'm not done. I have to get the y-coordinate. In order to find the y-coordinate, I'll need to plug this x value back into one of these two equations. If I go to the 2x plus 2y equals 14, I'll have 2 times 6 plus 2y equals 14. So 12 plus 2y equals 14. That means 2y equals 2, and y would equal 1. And that does appear to be pretty close to where my intersection is. Remember, without using a ruler, I'm likely to be off a little bit. If you're using a straight edge and grid paper, you should be able to see yours more clearly. Now let's look at a couple of application problems. All right, a dietitian needs to plan a diet for a patient using 2 different food combinations to meet the patient's needs. Each container of food A contains 2 units of additive number 1 and 2 units of additive number 2. Each container of food B contains 2 units of additive number 1 and 4 units of additive number 2. Find the set of feasible solutions graphically if the patient needs at least 10 units of additive number 1 and at least 10 units of additive number 2, and then we'll get the corner points of the feasible region. Okay, don't let this overwhelm you. You're going to need to think through the information that you have been given. And one of the best ways of solving this, in my opinion, is you want to write an equation that would have to do with additive 1, because we're wanting to find a certain amount of additive 1, and an equation that would have to do with additive number 2. So we're not going to write an equation for food A and food B. Instead, since they're asking us to find the feasible solutions when the patient needs at least 10 units of additive 1, that means let's get an equation that relates the information about additive 1. So if we go back and we look at food A, there would be 2 units of additive 1 and 2 units of additive 2. So if we want to think of the X's and the Y's then as food A and food B, we're going to let our X variable represent food A, and we're going to let our Y variable represent food B. So here's what we have. 2 units of additive 1 in food A is a 2X, plus 2 units of additive number 1 in food B is a 2Y, and we need at least 10 units of additive 1. At least means it's okay if it's more than, but it can't be less. So 2X plus 2Y has to be greater than or equal to 10. This is the tricky part, getting the equation. Now look at your additive number 2. So if we go back and look in food A, you have 2 units of additive 2. So that's also going to be a 2X. If I look at food B, I have 4 units of additive 2. So that's a 2X plus a 4Y, and the patient needs to have at least 12 units of additive 2, so that means that needs to be greater than or equal to 12. Once you have your inequalities written, the rest of this will be just like what we've done. This is going to be the part you have to practice, is getting the inequalities. Now, here's the other thing that they didn't tell you, but it's common sense. You're going to have your amount of food A to be greater than or equal to 0. You can't skip food A. You're also going to have your food B to be greater than or equal to 0. That's going to restrict us to the first quadrant. We can't have negative values of food, so we're going to have a positive amount there. Now, what's going to happen is we know we're working in the first quadrant from this right here. Now we need to come up with these 2 inequalities graphed on our grid paper here. So 2X plus 2Y is greater than or equal to 10. If I use intercepts, 2 times 0 plus 2Y is actually is going to be equal to 10, because I'm just looking for the intercept. That's going to give me Y equals 5. So I'm going to have the ordered pair 0, 5. I'm also going to have the ordered pair 5, 0, because if I put in 0 for Y, I get 2X equals 10, and that means 5, 0 is my x-intercept. Alright, so here's one line. Now, in order to decide where to shade, if I look at this original inequality, the 2x plus 2y is greater than or equal to 10, if I were to plug in 0 for x and 0 for y, test this side of my line that's below the line, 0 plus 0 is greater than or equal to 10 is not true. That tells me I'm going to have to shade on this side. Okay? Now, to get the next one, we're going to do the same thing. We'll put in 0 for x, so 2 times 0 plus 4y equals 12. And if 4y equals 12, y is going to equal 3. So I know 0, 3 is going to be one of my intercepts. To find the other, we'll solve for x after we put in 0 for y. And if 2x equals 12, x is going to equal 6. So 6, 0 is the other intercept. Now that I have my x and my y-intercept, oh my, sorry, I really missed the line on that one. Let me see if I can erase that and try again. It would be so nice if I could use a straight edge, but my iPad won't allow me to do that. Okay, so if I go from here to here, well, I'm still off, but maybe it's a little bit better. And what I need to know is where I'm shading. And so again, if I test by putting in 0, I can see I have to shade above this line. This is going to be the area that I'm shading. And remember, I'm still bounded in the first quadrant. So it's going to look like that. Now, would you say that this is bounded or this is unbounded? Well, this is clearly unbounded. How many corner points do you think we have? Well, there's actually going to be 3. There's one here, there's one here, and there's one here. So that means these intercepts that I found are going to be helpful. We're going to have the ordered pair 0, 5. That's this intercept right here. This is going to be the ordered pair 6, 0, because that went with our second line. So what I need to do is to find out where do these two equations intersect. And again, I think that is a good elimination problem. If you go back to what we have, 2x plus 2y equals 10. And then we have 2x plus 4y equals 12. All I have to do is choose one of these and multiply through by a -1. So if I multiply the top equation by a -1, when I add all these together, I'm going to have 2y equals 2, which means y equals 1. So I have the y coordinate in this ordered pair. To get the x-coordinate, choose one of these equations and plug back in. So if I were to take 2x plus 4 times 1 equals 12, I'll have 2x plus 4 equals 12. 2x would equal 8, and that means x is going to equal 4. So the ordered pair 4, 1 is the other corner in this graph. On this last example, Jenny knits 2 different capes. Now, she's not very creative because she calls one of them the Jenny, and it requires 3 hours of knitting and 7 hours to embellish the cape. The Helen model requires 5 hours to knit and 5 hours to embellish the cape. So we're supposed to find the feasible solutions graphically. If Jenny has at most 60 hours a month to knit the capes and at most 100 hours a month to embellish the capes. And then we want to find the corner points of the feasible region. So this is where we have to determine how to write these inequalities. And if you remember from our last example, I said you want to pay attention to the sentence that gives you a restriction of at most or at least. And in this case, Jenny has at most 60 hours a month to knit. So that means we're going to want to write one inequality that has to do with the time that she spends knitting. So if we look, think about what we did on the last example. We had the additive 1 and 2, and it was related to food A and food B. And we let our variables, our X and our Y, go with food A and food B. If our inequality is going to be related to knitting, and that means our other inequality will be related to embellishing, then our variables will have to be with these models. The X would be the Jenny model, and the Y would be the Helen model. So now we're ready to put together the inequality. For knitting, on the Jenny model, it takes 3 hours. So that's 3x plus the amount of time on the Helen that is used for knitting is 5 hours. So 3x plus 5y. And we know she has at most 60 hours a month for knitting. Well, if it's at most, it means it can be less than that, but she can't go over that. That is a less than or equal to 60. That's the first inequality. Now for embellishing, if you go back to the Jenny model, she needs 7 hours to embellish. So that's 7x for the Jenny. For the Helen model, it takes 5 hours to embellish. So that's a 5y. And she has at most 100 hours a month to embellish. So since it's at most, that's a less than or equal to 100. We also know that she can't have negative time or make a negative number of the Jenny or a negative number of the Helen models. So we're ready to see if we can get this on the graph. That, again, tells us we're going to be in the first quadrant. Okay, since the first inequality is 3x plus 5y is less than or equal to 60, I can either put this in slope-intercept form, or I can put it in intercept form to be able to graph it. And I notice 3 goes into 60 and 5 goes into 60. So let's use intercepts. 3 times 0 plus 5y equals 60. That means 5y equals 60, and y will be 12. So we're going to have the ordered pair 0, 12. And this means our graph needs to be extended up just a little bit. And that's where 0, 12 would be, right there. And then we'll come back and we'll put in 0 for the y. And we're going to have 3x equals 60, so x equals 20. Now, we've got an issue with that because I can't put the ordered pair 20, 0 on this graph unless I change the scale. So let's make our scale, instead of counting by ones, let's count by twos. And that will give us, mark on here so you can see, this will be 2, 4, 6, 8, 10, 12, 14, 16, 18. This will be 20 at the end. And we'll do the same on our y-axis and make that 2, 4, 6, 8, 10, and this will go up to 20. So now if we're ready to plot this graph, 0, 12 would actually be 2, 4, 6, 8, 10, 12 is going to be right here. And 20, 0 is going to be right here. So there's that inequality graphed. And since our inequality says 3x plus 5y is less than or equal to 60, if I put in my test point of 0, 0, that would make it a true statement. So I know that I want to shade below this line. Now let's get the other inequality on here. The 7x plus 5y is less than or equal to 100. So this one is a little more problematic just because 7 will not divide into 100 evenly. We can still try to use intercepts. We're going to get a fractional value, or we can do slope-intercept form. The option is yours. I think I will continue with intercepts though, because if I put in 0 for x, I have 5y equals 100. So y is going to equal 20. And that tells me 0, 20 is on my graph, which is going to be right up here since I changed my scale. Now, my x-intercept, because 5 times 0 is 0, is going to be the one that's fractional. And I'm going to get 100 over 7, comma 0. Now I need to estimate where 100 over 7 would be. So if I try to divide 7 into 100, okay, I'll go ahead and put this pen to paper so you can see 7 goes into 10 one time. 10 minus 7 is 3. 7 would go into 34 times, and then we would have a remainder of 2, so 14 and 2 sevenths. That means I'm just going to have to estimate about where this will be on the graph. So 14 is right there, and 14 and 2 sevenths means I'm going to be just a little past that on the graph. So I'm going to come from here to here. And again, I'll have to decide where do I shade. So if I put in my test point of 0, 0, I'll get 0 plus 0 is less than or equal to 100, which is true, and that means this is my region that I need to shade. Now this thing is bounded, and so we're going to have the corner points that we need to list for this feasible region. I know I have one of them right up here, which was 12, 0. This one right here. Okay, that was the first one we put on the graph. I also know I have 0, 0. I also know that I have this last x-intercept I put on the graph, which was 100 over 7, comma 0. But my other corner point occurs where these two intersect. So we're going to have to discover what the ordered pair is where they intersect. So I'm going to pull down, make a little bit of space, and we had 3x plus 5y equals 60, and the other one was 7x plus 5y equals 100. Well, I can see if I multiply one of these by a -1, I can cancel my y's. So I'm going to change all the signs in the top equation, and cancel the y's. -3x plus 7x is 4x, and -60 plus 100 is 40. So I get x equals 10, and that tells me that 10 is going to be the x value in that intersection point. Now I need to go back and find the y value. So if I have 7 times 10 plus 5y equals 100, 70 plus 5y equals 100, 5y would equal 100 minus 70 is 30, and y equals 6. The ordered pair 10, 6 is the last corner point, and if you look at your graph again, that is reasonable that that's where that intersection point is.